Alright, in this video I'm going to solve this problem. It's from section 1.2. It's the 13th problem, and it says here the bar graph gives the average atmospheric concentration of carbon dioxide. Estimate the yearly increase in the average atmospheric concentration of carbon dioxide. Express the answer in parts per million. And then B, we're going to write a mathematical model that estimates the average atmospheric concentration of carbon dioxide. C, in parts per million, X, years after 1950. If the trend shown by the data continues, use your mathematical model from part B to project the average atmospheric concentration of carbon dioxide in 2035. All right, so first of all, you can see that this is growing in a linear way. It pretty much, it's not exact, but it approaches the shape of a line. And so if we're talking about, let's see, well, in the first problem, we're talking about the average atmospheric concentration or the yearly increase in the average atmospheric concentration. That's what we call a rate of change. And so rate of change equals, and it's the change in y over the change in x. And the thing about rates is they have two different units, like miles per hour. In this case, it's so many parts per million per year. So let's go ahead and plug in the numbers. So basically, we're using 2 points. This point here is the point 1950, that's the time, which is on the x-axis, and 306 parts per million. And then we have this point in 2015, we're at 388 parts per million. And so we can use these points to find basically the slope or the average change over this time. All right, so normally you want to put the bigger number here. So the change in y was 388 minus the change in y here, which is 306. And this is parts per million. And then it's the year 2015 minus the year 1950. So you can put that into your calculator. Notice it does say round to the nearest tenth, and you should get about 1.3 parts per million per year. So on average, it's going up about 1.3 parts per million per year. So in part B, now we're supposed to write an equation that gives this average atmospheric concentration. It says in parts per million, X years after 1950. So they're using capital C for this atmospheric concentration. And think about it, it's in parts per million, X years after 1950. Well, in 1950, it was at 306. But each year, it's going to change by 1.3 parts per million. So 1.3, and again, that's per year, which we're calling here X. So basically, if X is 0, that's our starting point, because it does say X is the number of years after 1950. So this is when X is 0, this is when X is 1, and we just go from there. Well, actually, this is in 1960, so that's actually 10 years later. But basically, X is the number of years since 1950. And so you can use this formula to find out or to approximate the concentration X years after 1950. So it started at 306 and it's going up 1.3 per year. So actually to get the 312, although it's an approximation, you would put a 10 in here because that would be 10 years since 1950. All right, so this is our formula. So now in part C, it's saying if this model basically models what is going on here, we can project the atmospheric concentration or the average atmospheric concentration in 2035. So 2035, if you subtract 1950, remember that's time 0. That's when we started at 306. So let's go ahead and subtract that. 2035 minus 1950, and you get 85. And so C, so this is 85, is equal to 306 plus 1.3 times 85. It's 85 years after the starting year, which was 1950. So let's put this into the calculator. We have 306 plus 1.3 times 85, and I'm getting 416.5. I didn't actually put this in the computer. It may ask you to round to the nearest whole number, but if it's one decimal place, it would be about 416.5 parts per million. 416.5 parts per million. And that makes sense since it was at 388 in the year 2015, so this is reasonable. All right, and so that is number 13 in section 1.2.